Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 13th video lecture. And today I want to do probably just one theorem involving Riemann-Stieltjes integration. And this is a theorem about algebraic properties of Riemann-Stieltjes integration. And here it is. It says if f sub 1 is a Riemann-Stieltjes integrable function, and f sub 2 is also a Riemann-Stieltjes integrable function with respect to alpha on the closed interval from a to b, then f sub 1 plus f sub 2 will be Riemann-Stieltjes integrable, and c times f sub 1 will be Riemann-Stieltjes integrable, where c is some constant. So here I'll just say where c is an element of R. Okay. C is an element of R, so I should write a real number. Moreover, the integral from a to b of f sub 1 plus f sub 2 d alpha is equal to the integral from a to b of f sub 1 d alpha plus the integral from a to b of f sub 2 d alpha, and statement about that constant function, of that constant times a function, is the integral of a to b of c f sub 1 d alpha is equal to c times the integral from a to b of f sub 1 d alpha. Now, this is a more general version of a fact that we give in Cal 2, if you will, that if you're integrating something plus something, that's the same thing as the integral of the first guy plus the integral of the second guy, provided each integral exists. And if you're integrating a constant times a function, you can pull the constant outside the integral. So as I said, this is analogous to something we would say in Cal 2, but it's a more generalized version because we're talking about Riemann-Stieltjes integration. And we're going to prove this. So the proof is based upon that fact of a function being Riemann-Stieltjes integrable, provided that for given any epsilon greater than 0, there exists a partition of a to b such that the upper sum with that partition of that function minus the lower sum with that partition of that function is less than epsilon. So that's the fact that the proof is going to be hinged upon. And so we're ready to get started with that. So proof, we're going to let f sub 1 be a Riemann-Stieltjes integrable function, and f sub 2 be a Riemann-Stieltjes integrable function on a to b. And we're going to let c be an element of R. We're going to, for notation's sake, let f equal to f sub 1 plus f sub 2. And we're also going to let epsilon be greater than 0 be given. So we can use that criteria of the previous theorem that I just mentioned to show the integrability, or that f itself, if you will, is Riemann-Stieltjes integral. So first thing I want us to do is to make this observation. For any partition, let's say script P of A to B, and let's give a little bit more notation for script P. Say script P is equal to, well, symbolically it's got x sub 0, then x sub 1, and then it goes all the way up to x sub n. Of course, x sub n is B and x sub 0 is A. Then, so here's we're going to have two observations. The first one is that the infimum over any one of these subintervals, x sub I minus 1 to x sub I, of f sub 1 of x plus the infimum over the same subinterval, x sub I minus 1 to x sub I, of f sub 2 of x, that's going to be less than or equal to the infimum of f, the addition of f sub 1 to f sub 1 and f sub 2, over this same subinterval, so x sub I minus 1 up to x sub I. And the only time that I can imagine where they're going to be equal is when the infimum of f sub 1 and the infimum of f sub 2 happen at the same x value. Okay? Then we have equality. But that's a true fact. And we can have analogous fact about supremums, and that's what I'm going to write up next. And that fact, the analogous statement, is that the supremum over x sub I minus 1 up to x sub I of f of x is going to be less than or equal to the addition of the supremums of f sub 1 over those same subintervals plus the supremum over this subinterval of f sub 2 of x. Okay, from those two facts, we get the following. So we have that the lower sum with any partition of f sub 1 and alpha is plus the lower sum with this same partition with f sub 2 and alpha. That quantity is going to be less than or equal to the lower sum with this same partition of f and alpha, which is less than or equal to the upper sum with this partition f and alpha. But that's going to be less than or equal to, by this fact, and the definitions of upper sums. The upper sum with this partition of f sub 1 and alpha plus the upper sum with this partition in f sub 2 and alpha. So that's what we have. Now, since f sub 1 is a Riemann-Stieltjes integrable function, then, by that important fact, there exists a partition of a to b such that the upper sum with that partition, let's call that partition, let's give it a special denotation, let's call it p sub 1. The upper sum with this partition of f sub 1 and alpha minus the lower sum with this partition f sub 1 and alpha, that's going to be less than epsilon over 2, that's the positive number I'm going to take. And I can say a similar thing about the function f sub 2, because it's Riemann-Stieltjes. Okay, so I will say that. All right, since f sub 2 is an element of Riemann-Stieltjes integral functions, then there exists a partition P sub 2 such that the upper sum with P sub 2, F sub 2, and alpha minus the lower sum, P sub 2, F sub 2, and alpha, that's going to be less than epsilon over 2. All right. Now, what we do is we have two partitions here, P sub 1 and P sub 2. So to get the same partition involved, what we're going to use is the refinement. And so the common refinement. So we'll let P star equal to P sub 1 union P sub 2 be the common refinement. Of P sub 1 and P sub 2. Then, what we have is that the upper sum with P star of F sub 1 alpha minus the lower sum with P star F sub 1 and alpha, that's going to be less than epsilon over 2. And the upper sum with P star F sub 2 and alpha minus the lower sum with P star F sub 2 and alpha, that's going to be less than epsilon over 2. And that has to do with facts that we've talked about for upper sums and lower sums with respect to one partition and then a refinement of it. So what that generates is we have that the upper sum with this refinement partition and F, that's F now, and alpha minus the lower sum with this refinement F and alpha. Okay, that's going to be less than epsilon over 2 plus epsilon over 2, which equals to epsilon. So what that shows is that F is Riemann-Stieltjes integral. Okay, so the addition is Riemann-Stieltjes integral. We now want to show that the integral from A to B of F d alpha is equal to the integral from A to B of F sub 1 d alpha plus the integral from A to B of F sub 2 d alpha. Okay. All right. Before I move on, this fact right here with the F's as opposed to the F sub 1 and F sub 2, that comes from a fact that we had a string of inequalities that we had earlier in the work here for this proof of this theorem. Okay, so, it comes from the previous inequality we've done, and the facts that we had about the upper minus the lower sums for the F sub 1 and F sub 2. All right, so this is what we want to show next. And here's how we're going to do that. First of all, we're going to note that since the upper sum with this partition, P star, I'll say F sub j alpha minus the lower sum with this partition of F sub j alpha, same j. J is either 1 or 2. So since each one of these subtractions is less than epsilon for j f sub 1 and for f sub 2, they're both the same. Okay. we have that the upper sum of this partition in either one of the f sub 1s or f sub 2s, alpha, is going to be less than epsilon over 2 plus the lower sum. Now, that's going to tell us that the upper sum with this partition, this refined partition, f sub j and alpha, is going to be less than epsilon over 2 plus, now I'm going to put something bigger than the lower sum with that partition f sub j of alpha, and that is something bigger than it is the supremum of all those sets, which is the integral of f sub j d alpha. And that's what we have. So, since f d alpha from A to B is less than or equal to the upper sum, p f alpha, which is less than or equal to, okay, so this is a true statement by the definition of an integral. Remember, what this integral right here, is the infimum of all these types of upper sums. So for this particular upper sum, with this particular partition, it's going to be bigger than or equal to that integral. And that's less than or equal to the upper sum with p star, less than or equal to the upper sum of p star. This is f sub 1 of alpha plus the upper sum with p star f sub 2 and alpha. Okay. That's something that's been established earlier. We have, so since this is occurring, we have the integral from A to B of d alpha is going to be less than, let's see, this is epsilon, less than epsilon over 2, plus, this will be A to B of f sub 1 d alpha, so I'm using what's written right here, plus, then for this guy, it's epsilon over 2 plus the integral from A to B of f sub 2 d alpha. That's what it is. Okay? So, that says the integral from A to B of f d alpha, which we know exists, is less than the integral from A to B of f sub 1 d alpha plus the integral from A to B of f sub 2 d alpha, and then plus epsilon. Okay, well, since epsilon is an arbitrary amount, what we're saying is this number is less than or equal to this number plus any positive amount. What that tells us then is, since epsilon is greater than 0 and arbitrary, then okay, then we have, that implies that the integral from A to B of f d alpha is going to be less than or equal to the integral from A to B of f sub 1 d alpha plus the integral from A to B of f sub 2 d alpha. So we're trying to show these two things are equal. And right now I have that one of them is smaller than the other. If I can show the reverse inequality, then we have that they're equal. And that's what I'm working towards. And we can do that. So similarly to what we've done. So similarly, if we work with the lower sums, since the upper sum of P star Fj alpha minus the lower sum with P star F sub j alpha is less than epsilon over 2, then we have, okay, so that means that the lower sum, so that's what I'm going to write in terms of, the lower sum, I'm just solving this inequality for the lower sum, is going to be greater than, so I'm pulling that over there, this over there, so the upper sum minus epsilon over 2. Now, that says, that says that this lower sum is going to be greater than, well, look, let me get something smaller than this guy. And something smaller than this guy is the Riemann-Stieltjes integral of f sub 1, or f sub j, I should say, d alpha, minus epsilon over 2. Okay. Now, since the lower sum of P star f sub 1 alpha, I did before, plus the lower sum of P star f sub 2 and alpha is less than or equal to the lower sum of P star with f alpha since that's happening. Which is less than, wish I could have gotten all this on one line. The integral, so this lower sum of P star with F and alpha is definitely less than F d alpha. Let's say less than or equal to. Then what we have is the integral from A to B of f sub 1 d alpha plus the integral from A to B of f sub 2 d alpha will be less than I should have said something different here. I'm sorry. Then this got minus epsilon over 2 plus this integral from A to B of f sub 2 d alpha minus epsilon over 2. That's what should be said, so I'm making replacements here. Will be less than or equal to, or just less than, alpha of d alpha. So that says that the integral of f sub 1 d alpha plus the integral from A to B of f sub 2 d alpha minus epsilon over 2 is less than the integral from a to b of just f d alpha. And so this should be a minus epsilon, is what I should have written, because I'm combining those two. And again, since epsilon is greater than 0 and arbitrary, then that's going to yield that the integral from a to b of f sub 1 d alpha plus the integral from a to b of f sub 2 d alpha has got to be less than or equal to a to b of f d alpha. So that tells us, because we have two inequalities like that, but in opposite directions, that tells us that the integral from a to b of f d alpha is equal to the integral from a to b of f sub 1 d alpha plus the integral from a to b of f sub 2 d alpha. And that's what we wanted to show for part of this proof. And now we want to work with the constant times f sub 1 and its integration. Okay, so next, we want to show C times f sub 1 is an element of Riemann-Stiel's integral functions, and the integral from a to b of C times f sub 1 d alpha is equal to the integral from a to b C times that integral. So that's what we want to show. That's the second part of the theorem. Okay, so what we're going to do is we will divide this statement into two cases. So first case, I shouldn't say into two cases. We should say into cases in several cases. First case is where C is greater than 0. Okay, so here the first thing we want to notice is that if you look at the supremum of x sub I minus 1 up to x sub I, so over that end, if you look at the supremum of that end of the f of x's, well, by definition, that's greater than or equal to f of x for all x element from x sub I minus 1 to x sub I. Continues with that type of thinking. So what that tells us that we multiply both sides by this positive number c. So c times the sup over x sub I minus 1 to x sub I of f of x is going to be greater than c times f of x, and that's true for all x element from x sub 1 I minus 1 up to x sub I. And so that says that c times the sup over x sub I minus 1 to x sub I of f of x is going to be greater than or equal to the sup over the x of I minus 1 up to x of I of f of x. That's what that says. So we have this inequality. So this says C times the upper sum with the partition P, partition F and alpha, is going to be greater than the upper sum with the partition. I forgot something here. I made a mistake. I should have had a C here. So this right here has to do with the upper sums with the partition of CF. We're having F sub 1 here. F sub 1 of, all of these should be F sub 1s, really, because that's our function. You call it F or F sub 1, okay? So let's put F sub 1 to be consistent of alpha. Okay? That's because in the definition of these upper sums, we're going to be talking about the sups over these subintervals, and this is always greater than or equal to this one, so it's going to make this corresponding summations be this way. Okay? Also, we can do the same type of arguments with enthemums. So the enthemum of f of x over x of I minus 1 up to x of I is going to be less than or equal to f of x. So these are f sub 1s, I should say. F sub 1 of x for all x element of x of I minus 1 up to x of I. From this, we can continue on to introduce C. Remember, C is positive. So when I multiply by C, it's going to retain the inequality that's already been established. Namely, so C times the enthemum over the x of I minus 1 up to x of I of f of x, and here I should write my f sub 1, is going to be less than or equal to C times f sub 1 of x, and that's true for all x element of x of I minus 1 up to x of I. So, that means that C times the enthemum over all the x of I minus 1 up to x of I of f sub 1 of x is going to be less than or equal to the enthemum over x of I minus 1 up to x of I of C times f sub 1 x. So that yields that C times the lower sum with any partition P of f sub 1 and alpha will be less than or equal to the lower sum of the same partition of C f sub 1 and alpha. So that's the result we get from that. So, that says that C times the lower sum, P f sub 1 and alpha, is less than or equal to L L of P C f sub 1 alpha, okay, which is of course less than or equal to the upper sum, P C f sub 1 alpha. I'm going to continue down here, which is less than or equal to, that was the upper, C times, I should say, the upper sum with P f sub 1 and alpha. Okay, that's what we have. Now, those statements, that last thing that I've written, this last line, right here. It's a statement, okay? It's a statement that is true no matter what partition we're using. Well, I'm going to get a particular partition next. Well, in some sense, I'm going to get a particular partition. Partition we could say that exists is because a particular one that I'd like. So, since f sub 1 is Riemann-Stieltjes integral, there exists a partition, I'm going to call it p sub 1, such that the upper Riemann sum of p sub 1 with f sub 1 and alpha minus the lower sum, p sub 1, f sub 1, and alpha, that's going to be less than epsilon over c. And I know that's a positive quantity. That's why I can do that. So that's going to force c times the upper sum from p of f sub 1 alpha. So I'm multiplying everything by c. C times the lower sum of p sub 1, f sub 1 alpha to be less than epsilon. Okay? Now, I want us to move the camera back just for a second. Well, before I do, look, this is the statement involving the subtractions with the c's on the outside. Okay? So if we go back to this statement down here at the bottom, the c's on the outside here are at the ends of this inequality. So we're saying the subtraction of between these two guys, this guy minus this guy, is less than, their distance from each other is less than epsilon. That's going to make the inner guys, their distance from each other, to be less than epsilon. So, what that says is that the upper sum, so write this down, the upper sum with p sub, I didn't write this correctly up here. This should be p sub 1 here, p sub 1. With p sub 1, f sub 1 and alpha, that should be c, f sub 1. That's right, that's the inner one. Minus the lower sum of p sub 1, c, f sub 1, and alpha, that's going to be less than epsilon. So what we produced is this partition such that the upper sum with that partition of this function, c of f sub 1, minus the lower sum of that partition, c of f sub 1, is less than epsilon. So what that says then is that c of f sub 1 is a Riemann-Stieltjes integral function. We got one more part to do. Okay. Now, here's the last part we have to do. So also, since c times the upper sum with p, let's say p sub 1, f sub 1 and alpha, minus c times the lower sum with p sub 1, f sub 1, and alpha is less than epsilon. Then, what that says is that the integral of cf d alpha is less than or equal to c times the upper sum with p, f, and alpha, which is less than epsilon, let me write it down here, epsilon plus c times the lower sum with the partition p sub 1, f sub 1, and alpha, which is less than epsilon plus c times f d alpha. So that's what we have. So if we look here, we have, this will tell us that the integral, I should have A to B here. C times f d alpha is going to be less than epsilon, it's going to be just less than or equal to c times a to b f sub 1 d alpha. It should be f sub 1. Okay, that's what we have. Similarly, since c times the upper sum of p f sub 1, this piece f 1 alpha minus c times lower sum p sub 1, lower sum p sub 1, f sub 1, and alpha is less than epsilon. Then, okay, we have here, this is a c. We have that c times the lower sum, p sub 1, f sub 1, and alpha, this is similar to what we did earlier in the proof, is going to be greater than, here this will be c, forgot the c, is terrible. C times the upper sum, p sub 1, f sub 1, alpha, and it's minus epsilon. This is similar to what we did with the f sub 1 plus f sub 2 part of this proof, okay? So I'm skimming a little bit of the details here. Now, so what that gives us is the integral from a to b of cf sub 1 d alpha will be greater than c times the integral from a to b of f sub 1 d alpha minus epsilon. And so since epsilon was arbitrary and positive, that gives us that the integral from a to b of c f sub 1 d alpha will be greater than or equal to c times the integral from a to b of f sub 1 d alpha. And so, the integral from a to b of c f d alpha is equal to c times the integral from a to b of f d alpha in this case. What was this case? This case is when c was greater than 0. Now we've got to consider two more cases. That's when c is equal to 0 or c is less than 0. And in c less than 0, we'll do two subcases. Here, if c is equal to 0, well, that's easy. Then c times f sub 1 is equal to 0. And 0 is an element of Riemann integrable functions. Okay? So what we have in this case is that c times the integral from a to b of f sub 1 d alpha, well, that would be 0 times a number. And that's just equal to 0. And if we had the integral from a to b of c times f sub 1 d alpha, well, that's equal to the integral from a to b of 0 d alpha. And that's going to be equal to, we've said, is 0 times alpha of b minus alpha of a, which equals to 0. So in this case, So in this case, so when C is equal to 0, we get that C of A, the integral from A to B of F sub 1 B alpha is equal to the integral from A to B of C F sub 1 B alpha. Okay, now, the next case, here's case 3. That's if, so beforehand, we had case 2, okay, where C is equal to 0. Now for case 3, if C is less than 0, we will consider two subcases. One, if C is equal to -1. So as facts, let me write this down. These are things that are true. If you have the sup of minus F, supremum of minus F, that's equal to minus the infimum of F. And we proved, I believe, something similar to that in analysis 1. Okay? It didn't involve F, but it involved sets. Okay? And the infimum of minus F will be equal to minus the supremum of F. So, let's note there exists a partition such that, so the partition of AB, such that the upper sum with that partition, F sub 1 and alpha, minus the lower sum with that partition, F sub 1 and alpha, will be less than epsilon. Now, but we'll notice that the upper sum with this partition, F sub 1 and alpha, minus the lower sum with this partition, F sub 1 and alpha, what it's equal to the sum, as I run from 1 to n. Okay, so this difference is going to be the supremum value over the subintervals with respect to F sub 1 minus the infimum for F sub 1. That guy times delta alpha sub I, that's its definition, which is equal to, because of the facts that we listed on the left-hand board, this would be the minus m sub I of minus F sub 1, plus this would be big M sub I of minus F sub 1, delta alpha sub I. That's the facts that we have. And what that's equal to, so I'll just rewrite this, as the sum as I runs from 1 to n of the m sub I of minus F sub I minus the little m sub I of minus F, it's not I, it's 1, times delta alpha sub I and that's equal to the upper sum with this partition of minus F sub 1 alpha minus the lower sum with this partition of minus F sub 1 alpha, and we know that this guy, they're equal to each other, okay? But we know that this part is less than epsilon, so this part's got to be less than epsilon. Almost done. So what that tells us, so that says that minus f sub 1 is an element of Riemann integral functions with respect to alpha. Now, let's just note that the upper sum of the partition minus f of alpha is equal to minus the lower sum with the same partition of f and alpha. These things are the same. So the infimum over all partitions of this upper sums minus f alpha, I guess I should be writing f sub 1 here. F sub 1. Will be equal to the infimum of the over all partitions of minus L with this partitions of f sub 1 alpha, and that part is equal to the supremum over all partitions of here. This would be it should be minus the supremum. Practically bad of L of P of F sub 1 alpha. Okay. So what that says is that the integral from A to B of minus F d alpha is equal to, so that's this integral right here, that's this part, is equal to, this part is minus, with the supremum of the lower sums for this guy, is the integral from A to B, and this is just f sub 1, let's just say f sub 1. This is just f sub 1, where this guy was minus f sub 1, d alpha. So that proves what we needed to when C was equal to minus 1. And lastly, subcase 2, if C is less than 0 and C is different than minus 1, then C times F is really equal to minus C times minus F. Okay. And so that's where C, or I should say minus C is going to be greater than 0, and minus F, we've already shown, I mean, this is minus 1 times F, and F, let me put F sub 1 to be consistent. Minus F sub 1, right down here, is going to be an element of Riemann integrable functions, because f sub 1 was, and we just showed that in subcase 1 of this case 3. So, that means that minus C times minus f sub 1 is an element of Riemann integral functions. Okay, so why is that? Because this is Riemann integral, and this is a positive number in this case. And we did that in case 1, if you will, this part of the theorem. So that says that C times f sub 1 in this case is an element, because that's what this is an element of Riemann integral functions with respect to alpha. And if we look at the integral from A to B of C times f sub 1 d alpha, well, that's equal to the integral from A to B of minus C times minus f sub 1 d alpha. This is going to be positive constant. We can pull that out. So that's minus C integral from a to b of minus f sub 1 d alpha. This is a minus 1. We know we can pull it out from the previous subcase here. So it's minus c times minus 1 times integral of a to b of f sub 1 d alpha. And of course, that's just c times integral from a to b of f sub 1 d alpha. And that is the conclusion of the theorem. That's all we have time for today. Thank you very much for your time and patience.